Welcome everyone to another Select seminar. Today we have Alejandro Villoria from University of Leiden, who will be talking to us about optimization and synthesis of quantum circuits with global gates. So please, Alejandro, you want to get started?
Yes, thank you, John, for the introduction. And yes, so today we'll be talking about a new paper I had with my supervisors on a compilation algorithm that we have done using SEREX. So the idea of this project is to use SEREX calculus to take some input quantum circuit that we have and try to massage it in order to use it on ion trap quantum computers, specifically in certain ion trap quantum computers that have what we call global gates. So these global gates or global rotation gates, they are quite powerful because you are able to entangle multiple qubits with a single hardware operation. So in SEREX calculus terms, it would be something like we can see here on the right. So this is a composition of some phase gadgets of the same angle alpha. And the idea is that if you have a part of your circuit that looks something like this, so a series of phase gadgets with nothing in between, then this can be executed in the same time that it takes to execute just one individual two-qubit interaction that we can see here. So the idea is to create blocks of these phase gadgets in our quantum circuits in order to then reduce the cost of our circuit. And we do this changing the circuit extraction routine and adding some circuit rewrites in between each step of the circuit extraction. And also, if you have any questions at any moment, feel free to interrupt.
Yes, I have a question.
Yes.
When you talk about global gate, are you talking about gate that acts on non-adjacent qubit wires?
Yes, it doesn't have to be adjacent. So for example, here we can see that the second phase gadget, it acts on the first and the third qubit.
Got it, thanks.
Indeed. Yes. Yes, so the idea is to leverage the all-to-all interaction that you have in platforms such as ion trap quantum computers, but also neutral atoms. There has been a paper also somewhat recently that does something similar, but for neutral atom quantum hardware, in which they compile using what is called a multi-controlled phase gate. So first, we'll quickly go through the gate set that we're assuming here. So yes, we're assuming, first of all, single qubit rotations. These are not so interesting. So usually you have this R gate, for which you can recover the Pauli Rx and Ry gates, and some RC rotation. But more interestingly, we have the 2-qubit Mølmer-Sørensen gate that I will be calling MS or XX gate, which is some parameterized rotation on 2 qubits. And with this gate, you can recover, for example, the CNOT gate if you have some single qubit gates before and after, or the control C gate too. So this is what we're going to be using as our primitive. And with this 2-qubit gate, we're going to be building these global gates, which are a series of these 2-qubit gates. So the definition of the GMS gate, which is the Global Mølmer-Sørensen gate that we're going to be looking at, is it can be a bit convoluted, but I think that the best way to look at it is on a picture, which is what I was said at the beginning. So basically, if you have a series of 2-qubit rotations put together and you don't have, for example, a Hadamard in between, or a single qubit rotation that doesn't commute with these interactions at any point, then your hardware is able to take it and execute it in the time that it takes to execute just one. So these are executed all in parallel. So in here, we're assuming the restriction that we have to use the same angle for every 2-qubit interaction. But actually, there have also been demonstrations where you can have different interaction strengths between qubits. So here, I would like to just make the notation clear, since I'm using boxes here instead of Serx diagrams. It's not so clear to see. So this indices 1 to 2 means that we are entangling the first and second qubit, and 1 to 3 means first and third qubit, and so on. So of course, if we conjugate with Hadamards, instead of using the x-axis, we can use the z-axis, and we're going to be combining these two in our quantum circuits. But let's see how we use the Serx calculus for this. So first of all, if you're familiar with phase gadgets or Pauli gadgets, then this should be very natural for you. So the XX rotation and ZZ rotation is the Pauli X gadget and the Pauli Z gadget. And the global gates themselves are just a composition of this, as long as you have the same alpha on all of them. And we use Serx calculus for this task because the idea is to leverage the whole routine of taking a quantum circuit, making it a Serx diagram, simplifying it with just local complementation, pivoting, and so on. And then this will loosen the structure of the circuit in such a way that then when we're extracting gates, we want to extract them in this shape. So we want to, instead of extracting CNOTs the usual way or control Cs the usual way, we want to extract them in such a way that they can be compiled as a single global operation. So we go through the usual pipeline of taking a quantum circuit, we make it into a Serx diagram, so it looks like a circuit right now. And after doing our local complementation and pivoting, then it doesn't look like a circuit anymore, so we need to extract a circuit from it if we want to send it to a quantum computer to execute. And if you're familiar with circuit extraction, I'm sorry, because I need to explain it, because we're going to be changing how things work. So this part you would already know. So there are a few gates that you can extract when doing I would say, the standard way of doing circuit extraction. One of them are the CNOT gates. So the CNOT gates, what you do to extract them is that you go to your rightmost part of your diagram, you take the vertices from there, you call them the frontier, and then you're going to be applying operations on this frontier in order to simplify it and move it forward until you consume the whole diagram. If you want to simplify the connectivity of the frontier with its neighbors, you can apply CNOT gates. In this case, the vertex that is the control of a CNOT will get simplified. This is the one that we will operate on. As we can see here, we start with a V that has two connections, and then by applying these two CNOTs, we have only one connection to the vertex W. When you have a vertex with one connection, this means that it can be removed, and you remove it by applying a Hadamard gate, and this would move the frontier forward. And now we have W as our new frontier vertex, which we can remove the phase by applying an RC gate on that with that same angle. And if you have connectivity between frontier vertices, these are extracted as a control C gate, as we can see here. The W is connected with the vertex below, and we can remove this connection by applying a control C gate. Now, this is a well-established way of doing circuit extraction on Serx diagrams. And we're going to be changing this in order to extract the gates in a beneficial way for us, to compile them with what we call these global gates. So we do two things. We're going to be changing how the CNOTs are extracted, so they can fit better into GMS gates, because not every CNOT subcircuit can be compiled as a single global gate. So the idea would be to extract subcircuits of CNOT gates that can be compiled as a whole with one global gate, and then continue the extraction from there on. And then other gates, such as the control C and the single qubit gates, we will move in them around, doing peephole rewrites in order to compile things better. So let's see in more detail which circuit identities we're going to be using. So control C layers, for example, can be compiled always with just one global gate. This is quite easy to see, since a control C gate is equivalent to a set rotation, followed by two rotation gates on the set axis on single qubits. So they can always be pushed to the right or to the left. And then if you conjugate everything with Hadamard's again, you can have the XX version of this. Another layer of CNOTs that you can compile with just one global gate are what we call the fan-out gates. So a fan-out gate is basically a sequence of CNOTs that all have the same control qubit. These they look very nice. This on the second equation as a GMS gate, because then you only have Hadamard's before and after the global gate itself on the control qubit only. If you use the set axis here, then you would have Hadamard gates on the rest of the qubits except the control. As a side note, you can we don't use this equality, but you can also compile what we call fan-in gates instead of fan-out, which is the same, but instead of sharing a control qubit, you share a target qubit. This you can also compile with a single global gate. And you can find this kind of rewrites in the literature. But more generally, if you want to compile something that is a bit more powerful than a fan-out gate with a single global gate, you can go to commuting CNOT layers. And we can see this because so when we compile one single CNOT as an XX rotation, for example, you will have Hadamard gates on the control qubit. These Hadamard gates, they do not commute with the two qubit interaction. So if you were to have, for example, later a CNOT that has the control qubit as a target, then if you do this same circuit equivalence and you try to put the XX gates together, you won't be able to. So we can see that if we take the set of in a CNOT layer, if we take the set of qubits that act as controls and the set of qubits that act as targets, and these two sets are disjoint, this means that we can take this layer of CNOTs and always compile it with one global gate. So for example, a circuit like this that has 4 CNOTs with different controls and targets, but that the controls and the targets do not collide on a same qubit. This you can always use just a single hardware instruction for the entangling part, plus some single qubit gates. So in the case of the GMS, you would have then Hadamard gates only on the control qubits. And using these equalities and using this pipeline of taking a quantum circuit, making it into a Serres diagram, simplifying and then extracting, we can combine these two techniques in order to create some algorithm to compile quantum circuit for global gates, while we try to, of course, minimize the number of global gates that we get in the end. So one fact that actually you can find on the original graph theoretic simplification of quantum circuits paper, is kind of hidden there, is that you can actually always extract at least one vertex using a global gate. So in fact, all you need to always move the frontier forward is a fan-out gate. A fan-out gate can always be compiled with a single global gate. So if we create a process in which we take a frontier and we say, okay, we are only able to execute a global gate in order to advance it, then this will always have a solution. And the most basic case would be a fan-out gate. For example, the example from before, exactly to extract B, what we needed is a two CNOT fan-out. But of course, you would ideally not only extract a single vertex, but we want to extract as many vertices as possible with the least amount of CNOTs also, hopefully. So the idea is that, of course, we want to extract a single global gate, but if we can also reduce the number of CNOTs that we need for this would also be better, because then you have less qubits that are active at that moment. Yes, so what we're going to take is we're going to take the secret extraction algorithm, and we're going to be extracting global gates in the CNOT extraction part instead. And since the most powerful subcircuit that we can extract is a commuting CNOT layer, which is more general than just a fan-out gate, this is what we're going to be using. So let me just quickly show you how one does the frontier simplification part, how you can represent it as binary matrices. So basically what you do is take the adjacency matrix of the frontier vertices, which are the rows, and then its neighborhood, which are the columns, and you put a 1 in the case that there's an edge. And each CNOT becomes what is called an elementary row operation on this matrix. So for example, the CNOT over here is this matrix, which is the identity with just a 1 that indicates that on the control qubit 1, because this is row 1, we apply a CNOT with target the third qubit, and so on, which results in a matrix now with an extra vertex that we can extract, because there is only a single one here. So we're going to call what is the composition of this CNOT matrix G, our input matrix M, and then the resulting matrix X, just for the next slide, because we're going to be taking this problem and we're going to encode it as a linear program that will try to maximize the number of vertices that we extract with a minimum number of CNOTs. So what we do is we encode the problem. The idea is that we have the limitation that we can only extract commuting CNOTs on a frontier. And we want to maximize the number of extracted vertices. So in this case, we can define a maximization problem with some constraints. And these constraints, they capture the fact that we have some frontier with some connectivity, and then we can only apply certain row operations to it. Here, the maximization part means that we have a penalty C, which are the number of CNOTs that we're applying. And then the sum basically sums this binary variable set I that counts the number of extractable vertices, which we enforce to be at least 1. We know that this can be solved because we have seen before that all you need is a fan-out at least to extract one vertex. So there will always be a solution to this problem. Now, if we set this variables set I to 1 when there is a row with just a 1 and 0 otherwise, we can count the number of extractable vertices. And then our matrix G here is the commuting CNOT layer itself. So it will have one CNOT diagonal. And then this condition C5 over here, what tells you is that if you have a 1 in this, let's say row K column J, this means that you have a CNOT with control qubit K and target qubit J. So you're not allowed to have any ones on row J. So what this tells you is that you cannot have a qubit that acts as control and as target on the same layer. And the last condition, C6, what it is doing is just counting the number of ones. So this you can take it, you can put it on a solver, and it will output a commuting CNOT layer that maximizes the number of vertices that it extracts. And this then we can compile as a single global gate. So having this for the part that in which we extract CNOTs, we have to do more work on when we extract the other gates. So let's see. First of all, Hadamard gates and phase gates, what we do is we try to commute them past GMS gates that we have already constructed on the circuit. So then incoming CNOTs or incoming control C gates can be compiled together with GMS gates that already exist. So for example, you can see that here, if you were to have later a CNOT that has controlled the last qubit and target some other qubit except the first one, we would be able to compile it into the GMS that we already have by pushing single qubit gates to the side. Then control C layers, as we know, they can be compiled as a single global gate. But we have seen in practice that it's actually better to split them into two. So we split them into the ones that can be pushed aside into the last GMS gate that we have constructed and the ones that we can't. This is because if we go back to how one compiles a control C gate or control C layer with GMS gates, you have Hadamards on all qubits. What this then causes is that you cannot compile any more CNOTs to the GMS gate, because then now you have a single qubit gate that doesn't commute with the rest of the entangling gates. And lastly, the CNOT layers themselves, we merge them with the rightmost GMS gate. So of course, the layer itself can be merged with one global gate, but we always check if we can merge them with global gates that have been created before. If this is the case, then we try to merge them together. And here, in this case, I'm giving a more general case that I'm assuming that actually the CNOT layer itself is not necessarily commuting. This is because we split the algorithm into two. So in one, we use the linear program to solve the frontier simplification problems. But in later, we also tried with just using the algorithm that is implemented into P6 that just simplifies the frontier using some other algorithm, some synthesis algorithm. And then we compare between these two. So actually in this part, we do not assume that the CNOT layers are commuting. You can see here, for example, that if we were to extract these 5 CNOTs that we have here, these do not commute because the first 2 CNOTs on the right have a control that serves as a target later. So you will need 2 global gates to compile this layer, one for these 2 qubits and then one for these 3. But by pushing these 2 CNOTs into the global gate that we already have before, which we can do, then we save one global gate to compile this, because then we only need one GMS to compile these 3 qubits, these 3 CNOTs over here. Okay, so let me show you the numerical results that we have done. So we checked on different benchmarks. So we used Quantum bench, MQT bench, and then some quantum chemistry circuits. And we implemented 4 different algorithms to compare with. So first we have a naive algorithm that what it does is basically just goes through your circuit, and if it finds CNOTs that have a different support, so let's say they could be executed completely in parallel, but you're not aware of these circuit rewrites that we have here, then you just compile this as global gates, so just parallel CNOTs. Then we have the peephole rewrites that I showed in the previous slides, in which we move our quantum gates on to the right to compute them past GMS gates, plus the P6 algorithm of simplifying the frontier, and then one where we use the linear program plus the peephole rewrites. We also compare against Qiskit in this case, and we can see, for example, I think for here amplitude estimation is a good example that we see in most of the circuits, in which the best result would be the linear program, because it can always find the optimal solution on each frontier. Followed closely by then the peephole with the P6 algorithm, and then usually it goes Qiskit and then the naive algorithm. But in certain cases, actually, Qiskit can work better because it has a better single qubit gate optimizer. Because when we're performing these rewrites of CNOT layers and control C layers into 2-qubit interactions, we were creating new Hadamard gates, and we're creating new rotation gates. So these can really add up in the end to your circuit depth. We implemented also, like after this process of circuit extraction, a quick single qubit gate optimizer that reduces the single qubit gates quite a lot, but still Qiskit usually works better in this. So for example, in a quantum circuit like the GHC state here, that we cannot find a good solution for it because of how the CNOTs are arranged, then Qiskit can usually works better because it can reduce the single qubit gates better. So for example, this is how this GHC state circuit looks like. It's just a Hadamard gate and then followed by a cascade of CNOTs. So in this case, the algorithm cannot find a better solution than just compiling every single CNOT into a global gate. But actually, if you know that there is an alternative to make a GHC state in which you can actually just use a single fan out, that would be, instead of having all these CNOTs like this, you can have them all controlled on the first qubit and then using the same targets. This is an equivalent circuit, but going through the Serx calculus simplification and then destruction, since we are going through each frontier at a time, then we are not able to see this better solution. But this is this problem that we find is usually just in circuits that are very simple like this, or they are arranged in the CNOTs in a particular way that are not amenable for GMS gates. In general, the result that we have is that with the peephole and the linear program, we can reduce the time that it takes to simplify a circuit quite better. So here the time is in milliseconds. And we have, for example, the 2-qubit gate count, sorry, the entangling gate count, which is the number of global gates that we need, and then the single qubit gate count. In general, we have a lot less entangling gates on both on the peephole optimization plus P6 and the one with the linear program. But yes, in the case that your circuit is kind of like a counterexample of our use case, then it will not work so well. Yes, so what we have done is we have presented a circuit synthesis algorithm that works specifically for ion trap quantum devices. What we do is that we adapt the Strex calculus circuit extraction algorithm and we change it. So the CNOT extraction part, we make it as a linear program that encodes the exact behavior that we want, which is extracting commuting CNOT layers from your circuit. Apart from that, we add local circuit rewrites that group entangling gates together into global rotations. And compared to a naive algorithm and to Qiskit, the difference is quite significant. If you use these global gates, especially so you will get a lot of single qubit gates, but we have used the IonQ Forte benchmarks in which we have that entangling gate cost around 6 times more than a single qubit gate. So this is what they provided in their hardware paper for these benchmarks. And we show that even if we get more single qubit gates, the gain of grouping these entangling gates together as global gates is very much worth it. So one extension of this would be to allow for different interaction strengths for each qubit pair. So what I said before, if you have different alphas for each 2 qubit gate, then instead of extracting CNOTs, you could extract these phase gates instead as the paper that does the circuit optimization for neutral atoms does. We could leverage this technique. And I think in general, just exploring how modifications on circuit extraction to accommodate hardware restrictions, it can be quite interesting. So it would be nice to see more work on this side. Or also just thinking of the circuit extraction part or the part where we do the simplification as optimization problems or to encode this in solvers, I think we can benefit for it. And if you want to learn more, so of course, if you're not familiar with circuit extraction and simplification, you can go to the graph theoretic simplification for quantum circuits paper. And this paper by Pascal Basler of synthesis of and compilation with time-optimal multi-qubit gates really talks a lot about global gates and all the circuit equivalences that we can use or different sub-circuits of bigger circuits, how this can be compiled into global gates. Okay, I think that's it. And thank you.
Thanks, Alejandro. Nice talk. I'm guessing there'll be some questions in the audience, but I want to start with a question of myself. Could you go back to your table of results?
Yes.
Just so I understand the columns correctly, like SQG is like single qubit gates, entangling is number of number of GMS gates?
Yes, so SQG is the single qubit gate count, entangling is the number of global gates, GMS in particular, and T is the time, the time to execute the circuit.
Okay, so there's not time to find the optimization. That's like your estimated. Like, what's the cost model there for this time?
Yes, so we took it from the IonQ Forte paper, in which I think it's 110 microseconds for single qubit gates and about 670 for 2 qubit gates. And since the GMS gates, the global gates, take the same time to execute as just one 2 qubit interaction, we take this as the time that it takes to execute the global gate itself.
Okay, so a multi-qubit interaction is about 6 times more expensive as a single qubit gate.
Yes.
Okay, and do you sort of, if you have like, I don't know, like HS, is that the same cost as just H or something like that? Like, do you combine these single qubit gates?
Yes, so So in this case, what I do in particular is I convert these Hadamars as rotation gates, and then after I do the extraction, I try to push everything through commuting gates and add all the phases together. So these SQG are X and are set rotations, yes. If that's what you were asking.
And this reference 30 you have here, which paper is that?
Sorry?
This reference 30 that you have here, peephole plus 30.
Oh, yes, this is the Patel et al. Algorithm that is implemented into P6, the CNOT
Okay.
synthesis.
Right.
So this is what you would do to simplify the frontier instead of the linear program.
Right. So this is like with your heuristic of, oh, let's try to combine together these fan-out gates into a single GMS gate. Okay.
Yeah, so this would output layers of CNOT gates that are not necessarily commuting. So then you would simplify a frontier at some point, but then you would have a bigger cost of multiple global gates.
Okay. I saw there was a question in the chat by Leo Becker. How does the amount of qubits used in the global gates change error rates? So I'm guessing this is about your like error model or like how costly such a gate actually would be.
Oh yes, so in here we don't benchmark with the error models, but there are a few papers that discuss that. I think in our main text we also talk about it a little bit. But yes, I believe that I think the more qubits you have, indeed, you would have a worse performance. But also, for example, for ion trap quantum computers, where you also have to do, let's say, shuttling of ions and so on, you have to do less of these operations. So I think the gate itself, it takes the same time as a 2-qubit interaction, but you have a lower error rate, but it allows you to then skip some other hardware operations that have their own error rates in practice that sometimes we don't see in the circuit itself, like shuttling and so on.
Okay. Alex, you had a question?
Yeah, I guess that you'd somewhat answered this already. I'm just curious about this cost model where you count GMS gates as sort of 6 times as expensive as single qubit gates. Does that kind of approximately apply when you start including these multi-qubit GMS gates, or should these actually be counted as quite a lot more expensive than 2-qubit MS gates?
Can you repeat the question? So the global gates, this can be any arbitrary sequence of, let's say, phase gadgets, for example. So it takes the same time to execute because they are executing parallel because they commute. So it would take the same time.
Yeah, I guess my question was, is it really fair to count these things as the same cost as 2-qubit MS gates? If you're just accounting for time. And this could be, I mean, you said you didn't look at noise models. I guess this really has to do with the fact that maybe these are a lot noisier and you've got these multi-qubit operations. I'm not sure.
Yeah, I think in regards to time, it does take the same, at least from the literature that I have checked. But when it comes to error rates, it's quite mixed from the literature review that I did on that regard. There are some papers that they show that you will need better engineering than what we have now to get better results than just using 2-qubit gates, for example, for error correction circuits. But others claim that already we have an advantage with what we have. So it really, yes, I think at least when it comes to error rate, I haven't found like a particular conclusion of this. But when it comes to time, it does take the same time. So these are executed in parallel. So here we compare with time.
Okay, that makes sense. Thanks.
So I was also wondering, because there are these there's a series of papers where they find better and better ways to implement an arbitrary Clifford using I think right now it's a constant number of GMS gates, although this might require
Yeah.
variable strength and some ancillas, although I think the number of ancillas is also quite small.
Yeah.
Like I'm wondering if you use this kind of model where essentially like any Clifford is constant cost. Like I think they say something like you can do it with 6 or 7 GMS gates. You can implement an arbitrary n-qubit Clifford. I think it's like the result, something
Yeah, I
like
think
that.
it was 26 without
Or
ancilla
26.
qubits.
Okay.
Yes.
Yeah.
Yeah.
So I'm wondering how would that compare? Would that perform worse? Because I'm guessing in your case, like you're not extracting an arbitrary Clifford, you're just doing like a single layer to extract the next vertex. And this will look like a bunch of CNOT gates, which you can probably do a lot cheaper than using 26 GMS gates.
So if it's just a Clifford circuit and we feed it through this SX diagram pipeline, then yes, I think that the result would be cheaper. But well, it could depend though. But in here we're assuming we're actually assuming any gate set, any input gate set here. In that case, since this result is only telling you that a Clifford circuit upstart circuit can be compiled with 26 GMS, if you would go through your Strex calculus extraction and before you find any non-Clifford gate, you would perform this for every subcircuit. I don't think that this would work better.
Okay, yeah, that makes sense. Any other questions in the audience? So this linear programming thing, like what problem is that solving?
Yeah, let me show you. Let me go back. Yes, so it's kind of convoluted, I think, to just show it like this. But basically, what we're doing is that we're encoding the finding of, so we are inputting M to the linear program, and we are encoding find me a G that is a composition of elementary row operations such that we get an X with the maximum number of rows with just a 1.
And it's a linear integer program or like a Z2
Yes.
program. I don't know exactly how to call that.
So that's a linear integer program. And we have a penalty with it for the number of CNOTs also.
And is that just to like incentivize having small GMS gates?
Yes. Mm-hmm.
Yeah. So how long does this run on like if you have a couple of dozen qubits?
So we ran through a few benchmarks, and what I have put is on my laptop a timeout of 15 minutes to do the process, and it works quite well. I think that the main problem is not the qubit count, but the depth. I think because the more depth you have, then you have to run this program more times.
Yeah.
Which slows things down. But the qubit count itself, yes, of course, it also accounts. It also makes it slower, but the depth is the limiting factor here.
So I know that was not the point of your paper, but could something like this be used for the regular circuit extraction in physics? Because like right now, like we essentially do, as you say, the Patel-Markov-Hayes algorithm.
Mhm.
And like for small cases, even brute forcing, like what's the minimum number of CNOTs we can use to extract a single vertex? Like if we use this kind of linear programming stuff, do you think it would work in practice? It would reduce the CNOT count?
Hmm. I think in practice, yes, but you have to take into account that at least what I'm encoding here is just just the current frontier. So just let's say what we have at this step. So it can happen, and I have also seen in some benchmarks that you even if you get the best configuration for a frontier at this moment, then later on you actually end up with a worse circuit. In the sense that maybe you shouldn't have simplified the frontier at this point so much, because then you will have a more complicated frontier later on. I think that getting the best result for each frontier, at least for our use case of compiling with GMS gates, it does work better than the algorithm that is implemented in P6 right now, but it will not give you the optimal solution. You don't, because you also don't want to encode the whole diagram. It's not going to work. So doing it optimally stepwise works better, but still you don't get the best result. So, for example, I don't know if I have in the results here a case. Yeah, for example, you can see this circuit here. I don't know if you can see my mouse, DNN, with 51 qubits. Actually, no, wait, hold on a second. I don't know if I have a case in this screenshot. Oh yeah, this circuit, the trotter, this is trotter N4. So the fifth circuit, the Patel algorithm actually finds less CNOTs. So
Yeah.
it can happen, although you are getting the best result at each step, then maybe this is worse globally.
Yeah, I see.
But
I see.
in general, this is not the case, at least from the benchmarks that we have run.
But also like 4 qubits is very small, and that's like
Yeah.
would be far away from the sort of generic case, I guess.